In this video of How Does It Form, we're going to explore columnar jointing, a dramatic and often awe-inspiring geologic feature that can be seen around the world. In the Devil's Tower in USA, you can see a clear example of vertical column and joints between each column. The columns here are generally hexagonal. The Devil's Tower is 382 meters tall, with the width of each prism at around 2 meters. Columnar joints can also be just a few meters tall and only a few centimeters in width. These observations make you question, where else can we see columnar jointing? How do these natural geometric shapes form? And when did we first take notice of them? The first historical record of columnar joints were in Northern Ireland in the 1700s. The first mention of the Giant's Causeway was in a letter in 1693. And further observations and studies then published this drawing by Christopher Cole in the Philosophical Transactions of the Royal Society, London. A painting was then commissioned by the publishers and completed by Susanna Drury in 1740, and shows the impressive Giant's Causeway with columnar basalts in the background and people in the foreground for scale. Let's get back to the science and jump into volcanic eruptions and lava flows. When magma rises to the surface, a volcanic eruption can occur. One product of a volcanic eruption is a lava flow. Lava flows can be rhyolitic, andesitic, or basaltic. But how does this relate to columnar joints? Geologists that have observed and studied columnar jointing find that columnar jointing often form from lava flows. In an early published paper regarding columnar joints, Spry 1962 describes the morphological features seen in columnar basalts in the Columbia River, USA, and provides a hypothesis regarding its formation. Columns are characterized as long prismatic units with neatly fitting hexagonal symmetry, although it can be found as 5 or 7-sided or as 3 or 4-sided. These prisms are broken by cross fractures or transverse joints, where the simplest example is a plane joint perpendicular to the prism. In several columnar joints there are 3 divisions. The lower part is a lower colonnade, which is a vertical column with regular and straight morphology, above which is the entablature, with twisted and curved columns, and above which is the upper colonnade or pseudo-columnar, as it is described as being scoriaceous and crudely columnar. Spry builds on the work from the late 1900s and the early 20th century and hypothesizes that columnar jointing forms as a result of contraction. Lava begins to cool at the surface and is thought to cause spatially uniform contraction. Stress accumulates from thermal contraction once the temperature falls below that of elastic behavior. This creates horizontal tensile strengths at the surface of the material. It is found that when a maximal tensile strength is exceeded, joints form on the surface and create a disordered network. The strengths form normal at right angles to the cooling surface. If the contraction is equally spaced, it will form hexagonal features at 120-degree angles. But with variations in lava flow composition or thickness, this can cause variable-sided fractures. These joints then propagate downwards in increments and form the prismatic columns. It was found in Long and Wood 1986 that water infiltration plays a large role in forming key structures in columnar joints. Building on previous work, Long and Wood investigate differences in the cooling histories of colonnade and entablature in the Columbia River basalt flows. They divided flows into 3 different types. Type 1 is characterized by a highly irregular colonnade without an entablature. Type 2 has tiers of entablature and colonnade repeating. And Type 3 flows have a lower colonnade and a single well-defined entablature. Upper colonnades could be found in Type 2 or Type 3. Using thin sections of colonnade and entablature from the field and from each flow type to see interflow structures, they found that the entablature cooled at a faster rate than the colonnade, and this was based on the abundance and morphology of the last forming interstitial material between the larger mineral grains, the mesostasis. They theorized that this rapid cooling or quenching of lava could be from water infiltrating downwards from the joints and convectively cooling previously unsolidified lava in the center of the entablature. While we've been talking about basaltic columnar joints can also form in rhyolitic or andesitic lava flows, and they can be found all over the world, from Iceland to South Korea to Ecuador and India, and they've even found columnar basalts in Mars. So next time when you see a large columnar block in nature, you can tell yourself that these structures are not formed by fantastical beasts, but are in fact a wonder of structural geology.